Hi students. So welcome back to the lecture on state space modeling. So in the last lecture, that is lecture number 1, we understood the state space model basics and we applied state space modeling to a mechanical system, mass damper spring system. Okay. So here in this lecture, we'll see how we can model an electrical circuit using this state space model principle. Okay. So for that, I have taken a very well-known and familiar electrical system, which is nothing but an RLC series circuit. So the input to this circuit is EI of t. It is a voltage source. And if I apply this voltage source of EI of t to this electrical system, what will happen? I of t will try to vary, and because of this variation, ER of t, that is the voltage drop across the resistance, will start varying. EC of t and EL of t also will start varying. Okay, so therefore, when I give this input, there are 4 variables which are going to change. And of course, apart from this, there will be another variable, charge, Q of t also. Okay, so Q of t is also a variable there. The charge in the stored in the capacitor or flowing through this inductor or whatever, that is also going to vary. So therefore, that is also a variable. Okay, time dependent variable. So now the question is, what are the state variables that I can choose from this set of variables, and what is the output I can take? Okay, so we'll deal one by one. We'll just see what are the state variables I can choose from this. I got 5 variables if you look at I of t, R of t, EC of t, EL of t, and Q of t. The first question to be answered is about the number of state variables. Okay. To answer this question, you should understand why the variables doesn't change instantaneously but take some time to vary. Okay, so why this variation of these variables with respect to time comes? They do not vary instantaneously. Okay, it is because of the energy storage elements. We all know that. So, how many energy storage elements are in this circuit? There are 2 energy storage elements, that is capacitor and inductor. So the first principle is the number of state variables for a system is equal to the number of independent energy storage elements. Obviously, see, even though I have got 5 variables here varying with respect to time, I don't need to take all these. The number of variables is either going to be 5 or less than that. How do I define the state variables? It is the minimum number of variables, knowledge of which is necessary to describe the system. So it is basically equal to the number of energy storage elements. So in this circuit, it is CLL. So the first question is answered. For this system, I need 2 state variables. Now the question is, what are the state variables I can choose from this? You can choose anything. Okay, any 2, but to make it a bit systematic, usually how we take is, as explained in the previous lecture, the variables which affect the energy stored in these energy storage elements. Okay, so in the previous case of mechanical system, energy storage in the mass was affected by the velocity, and the energy storage in the spring was affected by the displacement. So that is why we took displacement and velocity as the state variables. Okay. So here also let us see what variables we can choose. So for the first energy storage elements, C, energy stored in a capacitor is given by of C V square, where V is the voltage across the capacitance. Here the voltage across the capacitance is EC of t square. Okay, and the energy stored in the inductor is half of t square. Okay, so E of t square. So it's very clear now. The energy state variables I can choose are EC of t and I of t. Okay, right. So it's clear. So the number of state variables is decided and the state variables to be chosen are also decided. So now let us come back and try to find out the state equations for this system. So this is the expression or this is the equation corresponding to this electrical system, which is written using KVL, that is Kirchhoff's voltage law. Input voltage is equal to sum of all the drops in the elements, ER of t, EC of t and EL of t. Okay, so having understood or having identified the okay, so state variables, we'll just write the state variables. X1 is equal to, let me write it as EC of t, and X2 is equal to I of t. So therefore, usually the voltage across the capacitance and the current through the inductor. I of t is the current through the inductor also. So the voltage across the capacitance and the current through the inductance are taken as the state variables. Okay, for any electrical system. That you can use it as a basic principle. So now I have to write the state equations. So therefore there will be two state equations. The two state equations will be dx1 by dt. So we all know that the state equations are the equations which describe how these state variables vary with respect to time. So other one is dx2 by dt. What is dx1 by dt? That is dEc of t by dt, and this is di of t by dt. Okay, so ER of t is R into I of t, EC of t is, this is obvious, well known, right? Is there any possibility that I can get any of this state equation from this using this? Yes, EC of t is here, right? 1 by C I of t. And EC of t has to be written in terms of input and other state variables. Okay, so shall I differentiate this? Okay, so this is energy storage. Okay, so from this, if I differentiate this, I will get 1 by C I of t. Alright, okay. So first state equation is ready for me. And the second equation, from where I will get, okay, I'll just erase this, all this. This one I will erase. So this is the equation, right? Now let me write this equation in terms of the state variables. EI of t is equal to ER of t. What is the expression for ER of t? R into I of t. So I can write it as R into I. EC of t, should I replace with this any of these expressions? Not necessary, because EC of t itself is a state variable. So I can just write as it is, EC of t. EC of t. Okay, so plus EL of t. So what shall I do with EL of t? EL of t is not a state variable. So I should write in terms of the state variable, that is I of t is a state variable. So in instead of EL of t, I can write it as L into dI of t. So I'll just write till tau ei of t is equal to r into I of t plus ec of t as it is because it's a state variable and L into di of t by dt. Okay. So can I get this di of t from this equation? Yes, I can get. Therefore, it is ec of t is my x1. So therefore, I will write it first 1 by L minus 1 by L ec of t minus r by L I of t plus 1 by L ei of t. Alright. So now I got all these two state variables I got, and I will just try to represent these state equations in a matrix form. Okay. So shall I do it? So therefore, yeah, I will write them as so dx1 by dt. So this is so the first equation is ec of t by dt, that is x1 of t. Okay, so x1 of t is equal to, okay, so what is 1 by c I of t. I of t is x2 of t, and x2 dot, that is di of t by dt is x2, that is x2 dot is minus 1 by L x1 of t, okay, minus r by L x2 of t, then plus 1 by L ei of t, which is the input. So in matrix form, if I write x1 dot x2 dot is equal to so this is x1 x2, there is no x1 term here, so 0, it is 1 by c, and here it is minus 1 by L, and here it is minus r by L x2. Okay, so plus the first equation, there is no e of t, ei of t, no input, 0. This is 1 by L ei of t. Okay, so these are the state equations. I have just written this state equation in a matrix form. Fine. Okay, so we got the state equation. I'll just erase this part. Now, let us come to this output equation. What are the possible outputs I can take from this circuit? I can take I of t as this output. If I of t, I take it as an output. My y of t is equal to I of t. I of t is x2. Okay, so what is my output equation? Y of t is equal to 0, 1. What I will do is I will take I'm going to take both I of t and EL of t as my outputs. Okay, so two outputs I am going to take. So the first output I am going to take is I of t. So I of t is nothing but x2 of t, and the second output I want is EL of t. Okay, what is EL of t? It is EA of t minus ER of t minus EC of t. So I will write it as minus EC of t minus ER of t plus EI of t. Obviously, EC of t is a state variable. I can leave it untouched, whereas ER of t is equal to R into I of t, because I have to write everything in terms of state variables I have chosen, and E of t is the input. I can just leave as it is. Okay, so this is my second output, y2 of t. So can I write this in matrix form? So y1 y2 is equal to, so please note that this is x1, this is x2. Okay, so this is y1 is only x2, 0 1, x1 x2, and y2 is x1 is minus 1, okay, and this is minus r. Am I right? Minus r into x2 is I of t. Okay, thus the first equation there is no input, 0, and in the second equation it is 1, EA of t. So I got this state equation and the output equation. Please note that usually the state equation is written first and the output equation is written next. Okay, so which is the A matrix here? X dot is equal to A x plus B u, okay, and y is equal to C x plus D u. So this is matrix A, that's the state matrix A, and this is the input matrix B, and this is the output matrix C, and this is the feed forward matrix D. Okay, so please note again, the state equation has to be written first and the output equation has to be written next. Okay, so therefore this equation, so this, let me say this is 1 and this is 2. So this equation, this sets of equation is what I call it as the state space model for this electrical system. Please notice this states what I have chosen need not be the same. You can very well try with by choosing other state variables. For example, you can take Q of t as the state variable, Q of t and I of t as the state variable. That is also a very good choice. Okay, and you can try see what is going to be the changes in the equation. And the output also depends, you can take either one of the state variables as output, or of course you can take some combination. Say for example, the voltage across the resistance and the capacitance, you can take it as an output. So the entire output you can take as an output. So in that case, ER of t plus EC of t is equal to EA of t minus EL of t. So that is how you have to change. So your matrices will have a change depending upon the input of output. Depending upon the outputs you choose and depending upon the state variable you choose, this matrices will be different. So the bottom line is the state space model is not an unique one. Okay, so of course you will see that all the systems will represent the same system, but the this selection or the model what you get Of course, it's a unique model. All the models are representing the same system, but it need not be, the matrices need not be unique for that. Okay, so that is the point. So in these two lectures, 1 and 2, we have seen how to model a mechanical or electrical system using the state variables, okay, with the help of the simple systems. The next lecture, we will go for a little more complicated, not very much complicated, little, some other systems which will have more number of energy storage elements possibly, okay, and see how we can model such systems. Okay, thank you.